Hey, I'm Bob Watchorn, geologist of about 50 years standing now, and I first started in Tasmania in 1968 working in the tin mines up at Rossard and Storys Creek, and then went to the School of Mines in Kalgoorlie through to 72, worked with Western Mining from 71 through to 99. And then was a consultant from 99 to pretty much now, winding down. This talk today's on, well, I've called it underworld time travel, because effectively we're not going to do any surface exploration at all. We're going to go underground. The underground will be from about 60 to about 300 kilometres depth using seismic tomography. I don't think this is paradigm changing research, as geologists amongst you will realise as we go through it. So put on your hard hats, we're on a tight time schedule here. And we're going to examine the lithosphere under Australia, North America and North China, compare the lunar mares with those places. Find out about the mineralisation in those places, and I'll be presenting new exploration targeting concepts, actually based on what you can see as opposed to theories about what might happen under the earth that so far nobody's actually been able to show. What I can show you today actually happens under the earth. The basis for the research is seismic tomography, which, although I've been doing this research in enhancing and looking for minerals for about 30-40 years, I've only really used seismic tomography in the last year or so, and it's good stuff. So we'll be travelling from Australia. We're going to look at we'll look at Australia overall, then the Yilgarn, Pilbara, Mount Isa, Olympic Dam. We'll travel to North America. We'll look at the Abitibi Belt, which was actually very surprising, and then across to North China to finish. Sneak preview of some of the work that I've been doing. People ask me can you have a look at the area that I'm in? So each of these plans with all the big rings on it is actually the tomography of those continents at about 60 or so K down. So the current paradigm or way of thinking is that very few pre-4 billion year old rocks survive. Mine is that huge areas survive under all the continents, and they not only survive, they survive intact from 4 billion years ago. The moon, you can see very similar structure, so I'll go into that a little bit more. So geology of Australia and its correlation to the rings. So the small areas are brown, they're the Archean. Effectively you'd say, well, you know, if you only look at the crust, you'd say that there is very little old rock left. And I would bet that 80% of geologists don't know anything about the lithosphere. They would be like me 1 year ago. 49 years experience, and I had to be told what the lithosphere was. So the lithosphere is actually up to 300 or 400 kilometres of solid rock that sits under every continent. The geology and the rings that are underneath, the rings that are underneath are basically undeformed. They overlap, so they form concurrently. The crust is what they call accreted, so they say, and it is. It's started in the west and accreted younger and younger and younger as you go to the east. And that's only the top 50 kilometres or so. Tomography, seismic tomography, the definition, it resolves lithological parameters, in particular the short wave seismic waves by comparing the waves in various areas. So the actual slow waves, wet rocks like sediments and lavas that come up under the water, and the fast stuff is igneous rocks. These are the actual, this is the data that I've used to look at Australia, from 75 to 300 kilometres, and 2 sections, in fact 3 sections I used. It does open up a whole new world of geology, and because it's opening up geology, you're opening up exploration opportunities if you look at it right. So you go from this, that's, I'm not saying that's as good as most scientists get of Australia, but they really can't get less than about 50 to 100 kilometre resolution on these structures. I can get them down to 5 kilometres. I can just keep enlarging and enlarging this stuff until I can get right down to 5 kilometres. I can look at all the structures as they go up through the Yilgarn. You can also see strong tectonic zones running through, effectively suggesting, well, not suggesting, telling us that this lithosphere under Australia is actually still in situ, and it's also undeformed. Hasn't all been messed up. There is no plastic mantle under Australia until you get down to 400 or 500 kilometres down. Unlike what most people think, they think 60 kilometre crust, moho, plastic mantle, it's rubbish. The actual cross section here is cross section 20 degrees south, and the tomography there, if you look at that closely, effectively there isn't any accretion or sliding over of blocks. It's effectively one big block from side to side. That's pretty much the to scale. The crust would just show up as a tiny little thin line at that scale. This is the rings there are the rings that I can see, and we'll be going through this in more detail in the Yilgarn and the Pilbara, up at Mount Isa and down in the Gawler Craton in South Australia. The thing to notice, and I've noticed it in North America and at China as well, that the biggest ring structures are very, very similar to the ones on the moon, or the one that you can see on the moon in particular, down to the point where the centre of it is actually filled with younger rocks. On the moon, it's the actual structure happened at about 4 billion years ago, but the actual infilling lavas right down to 1 billion years ago. So the moon is tectonically active for 3 billion years after the impacts that caused the big craters there. And so Earth is the same. And like the moon, which it's been rigid, and you can still see the round circles, on Earth the actual impacts solidify the actual crust instead of the other way around, or solidify the lithosphere. The actual lithosphere gives off more heat than the impact has imparted as kinetic energy, and therefore it's going to cool it. And that's the reason why the lithosphere is so deep and so rigid. This is another 75 kilometres down, 150 kilometres deep. So I've given a sort of an arbitrary, but it's not really arbitrary, time frame for each level. So corals grow at about, so if people say, well, you know, you're trying to tell me that Earth's Earth during impacts has actually had a 300-kilometre skin of lavas put around it. That sounds a bit too much. Well, 300 kilometres of lava over 300 million years actually equates to 1 millimetre a year. So I'd say that we're looking at a lot more than 300, and a lot's been eroded off. In this particular slide, there's 3 different types of ring structures. A big one up here which surrounds this here, this centre here, which is a very woolly looking structure, very digested. The second impact or giant ring structure has got an intermediate looking texture, and the latest ones have got a very brittle looking texture with the same northeast and west-northwest structure. From that, I'm saying that all these impacts actually happened during the late heavy bombardment, which went from 4.1, 4.2 to 3.8 billion years ago. So I'm just allocating 100 kilometres depth with, or 50 kilometres depth with 50 million years. And so therefore I'll get my time frame for each level I'm looking at. That's just a sketch of the different craters. I really haven't got time to explain it in great detail, otherwise we'll just run miles over time. But effectively that's the situation. So I've got 2 methods of enhancing the data. One is a structural method, and the other one's domainal method. This is the domainal one, so you're highlighting areas of different domains. The structural one is where you're just looking at all the detailed structure. And that's with about 9/10 of the stages left off. This is the way I enhance it. I go from that, enhance it a bit, you'll see a little bit of structure there. Go down, you'll see a little bit more structure, and then you go down to that and you end up with this after about 20 or 30 iterations. It's a bit of an art doing it. I've actually sent the methodology out to lots of geologists, and a few say that they've actually managed to crack it and they're delighted, and others say it's just so frustrating. How did you ever have the patience to do it? This is the same 150 kilometre depth, showing the, I'm actually going to break with tradition and call them impacts, because I'm absolutely certain that they're impacts and not just giant ring structures. I know I'll cop a heap from purists, but you've got to be a little bit sure of your convictions. And the reason I'm sure that they are impacts is that the plan morphology is exactly like an impact. It's got a high centre and a series of rings around them. The sectional morphology, so that Y there is actually of this impact here, and the actual, so you've got a set of rings there, and when you see it in section you've got a set of arcs that face downwards. So if you look at that, you've got a series of bowls that face downwards, and that's the same on the big one in the middle. The arcs actually face downwards. The actual core of the impact is above this level, and so looking from the other side, you've actually Y is over here, exactly the same. So total consistency in results in plan and section. And it does suggest that the geological processes are acting downwards, which, well, there's only really one methodology of forming these structures, and it's not by plumes coming upwards or diapirs or dikes or stocks, particularly as they're over 1,000 kilometres in diameter. They are impacts. Now we go down another 150 kilometres. So I've done them on about every 75 kilometres. I've missed a couple out due to time constraints. So we're now down probably near the base of the lithosphere, although for all I know it could have still gone another 300 kilometres down because the structures and things are still like really rigid at this level. There are rigid structures running everywhere, which we'll see as we hone in on each area, the Yilgarn, the Pilbara and Mount Isa and that. So if you actually read that, I won't say it because, but the last bit, the late deformation, the boundary between the upwelling mantle and the remaining impact structures is actually the locus of where mineralisation is, which you would expect because that's going to be the tectonically most active zone. That's the same thing again. I'll just, I suppose just as an example of how you can see them, there's that one there. If I oscillate backwards and forwards, I don't know how it's coming out on that, but you can sort of see the shadow of a ring, and that actual ring, that shows up through a lot of levels. Now, some of the rings structures, they go right from the surface right to the bottom. And the ones that go right to the surface, obviously, are the latest rings because they happened at the end. But even those ones are actually, they're actually big, and even those ones go clear through 300 kilometres down, really without actually changing any. They don't seem to change diameter. When you hear about craters and things, and you know, most people try and fit a 300 kilometre or 200 kilometre diameter crater like Chicxulub in America, Sudbury and Vredefort in South Africa. They try and see all of the crater in the 60 kilometre deep crust. Well, that's just nonsense. Because craters just don't work that way. You've actually got to look into the lithosphere. This is how I believe the genesis of Australia, or the genesis of the lithosphere under Australia, is formed. So if you go from the surface, actually the surfaces actually shows quite a lot of those rings, particularly in the older rocks, down to 175, 150, 225, 250 and 300. You'll actually see there's huge rings down near the bottom which don't appear to get up to the top. I believe they're the first late heavy bombardment impacts that actually formed the original lithosphere, and then the rest just pile on top and get built up through lava. Like what you see in the mares on the moon, exactly the same process. And the moon has got layer upon layer upon layer of mares as well. The ones that you see on the top there are just the last ones. They've got about 3 that they know of that they can actually see. So I plotted up a bit of structural geology, if that be the right word, from the top to the bottom. And as I said, the footprints don't change from the top to the bottom of these large impacts. And so while 300 kilometres might seem quite deep, that's actually the thickness of it across the width of Australia. And the impacts, it's just going straight down. I guess this leads to comparisons with the moon. The moon, that's Australia at 200 kilometres depth. Probably should have used that one at 150. It's much more like what the moon looks like. So pattern is very similar. The density, the ring structures are very similar. That's a big ring structure. That one set on A. And so I'm definitely saying that the lunar mare. Well, we know the lunar mares formed during the late heavy bombardment. and I'm saying, well, Australian lithosphere formed at the same time. There's only one time in the whole history of the inner solar system that this happened, and that's 4.1 to 3.8 billion years ago. No time before and no time after has there been conditions that will give you that these huge, great big impacts. That's a comparison between the moon here, pretty much as you see it on the night sky. That's using structural enhancement. You can see lots and lots of structures on the moon, and various layers of circles, which are the craters that have been infilled with lava. This is the Pilbara up here. It's a very strong ring up in the Pilbara, and down in the Yilgarn they're strong, but they're much less obvious. There's the centre of a major one there, and then running around there, and another one sitting in there. If you draw up the rings and draw up the linear structures, they're very similar pattern, as you'd expect them to be, because they're both rigid bodies at that time getting impacted. By proportion, the moon, you know, is a third the diameter of Earth, but Earth's got what, 5 or 6 times the gravity of the moon, so the impacts are going to happen, are going to hit twice as hard. So the result is probably the fact that they will look very similar. And to me they look almost identical in structure. So now come down to the Yilgarn craton, and that's the it is an enlargement of the previous slide where I showed the rings. That's the moon up here. So there's a big impact there, then a lot of little ones, and there's bigger impacts that you can see in behind. The thing is, they're all circular on the moon. There aren't any impacts that are not circular, unless they've come in at a glancing angle. On Earth, there's lots and lots. There's circular ones, and there's lots of ones that are weird shapes. And I'm supposing that these later impacts that have that are the big circular ones have come in and hit a lithosphere that's actually is not rigid at that point, and so the earlier impacts are getting tectonic movement. I won't go through Boyle's second law of conservation of energy again. Needless to say, it's just like the lithosphere is the spray can, and when you spray off energy out of the spray can gets cold, and that's how the lithosphere solidified. Cross section through from Mount Magnet. Mount Magnet through to Gruyere, out past Gruyere. There's, so the top one's a plan with the rings drawn on it, and the middle is the seismic sections. You can absolutely definitely see that the crust is segmented and ramped up, which is the accreted way that the crust is formed. But the lithosphere underneath, while it still does have ramps, there's many structures that just go straight through. And you can also see the, not quite so well on this one, but on some of the later ones, you can see the big bowl-shaped structures that sit in there, going right to the bottom. Getting to the more interesting part for economic geologists, these mines that are plotted on there, they're the actual positions on the surface of the main mines. I've just drawn the main mines onto the onto the 75 kilometre depth tomography. So this has been enlarged again, but you're still not losing any resolution of your structures. I can enlarge that right up to round Leonora. I can enlarge that little ring that sits there right up, and you can still see other structures coming up from underneath. On this particular plan, the mines are located on the linear structures. That's sort of like Ravensthorpe, Southern Cross, and while you'd end up going through Kirkalocka and Mount Magnet and up through there. This one's Golden Grove, Mount Gibson. You've got them running across this way, Tropicana, and you run up that way. If you look at the more detailed mines, when you've got a lot of them, you can actually see that there's about 3 or 4 linear directions that the mines sit on. They also sit on, and I mean exactly on the big ring structures. They run right around there, they run right around there. I've been reporting on or writing papers on these ring structures for a few years now. Might say deafening silence, but it's been good fun. So that mineralisation is 3 billion years old. So presuming that the actual these structures, ring structures, actually happened before 3.8 billion years, which they did, because the only thing that can do them is the late heavy bombardment. Then these mines are sort of 800 million years afterwards, suggesting lots and lots of ongoing movement. This is most important diagram showing the same seismic section enlarged a bit, and with the structures coming right up from the bottom, vertical structures cutting right through all the other ring structures. And lo and behold, the main ones actually do line up. There's a zone between there and about there that, when you look at it without all this stuff on it, is actually a lot darker. Actually, sorry, between about there and there. And that's the main mineralised belt through the Yilgarn. And the actual, when you look at the crust, you can see fan or flower type structures at the top of these big structures going down to 300k. And all of those sit under the main mines, and all of them sit under antiforms in the top of the crust. And there's antiforms. So there's Laverton, there's the next big discovery, there's the next big one, and there's the next big one. There's Gruyere, which has just been discovered. Lots and lots of them. No reason why that flower structure is any worse than the one under Laverton. So it gives us a good idea of where to look. As flower structures not anywhere near as well developed in the Murchison, but they're there. This is a section looking across from Golden Grove across through Wiluna. And the reason for showing this one is that basically it's a 3-way verification of my method of data enhancement. So we've actually got the north-south Norseman-Wiluna line coming up through here. Well, not quite north-south, but nearly. And that runs straight into a very large, well, the biggest vertical, I'd say, fluid channel. Everywhere that I've seen these dark valleys, they're fluid channels. So you've got the one there, you've got another one there, running up that sandstone line. Another one over here running up the Golden Grove line. Another one there. And I think if you look at all of them, they all correlate with major structures that are coming through. So a big major broken structure running up through there, you've got a big major broken structure extending down 300 kilometres. This slide's basically the other concept I've come across while I've been looking at this is that there's like some of these ring structures or impacts of like they're the only source of a particular metal in all of the Yilgarn. So this, all of the uranium, primary uranium anyway, if you call Yeleri primary, because it comes off a granite that's right there, they all sit in the Barrambie giant ring structure. So I'm basically saying that the gold and uranium and vanadium, all of the big vanadium deposits in WA sit there. That these particular impacts have particular metal characteristics, and we know that the meteors do. They're all different. They've come from different parts of that supposedly Mars-sized protoplanet that Jupiter exploded on its journey into the inner system during the late heavy bombardment, and it's going to have the same characteristics as if you blew up Mars these days. So we go down to 300 kilometres in the Yilgarn, big brittle structures all over the place, and all these funny looking white blobs all over the place. Those funny looking white blobs are actually what all the mines sit on. Nearly every single decent mine that's sitting 300 kilometres above this particular spot sit on these white blobs that sit on the brittle structures down at 300 kilometres. Norseman, Kalgoorlie, Menzies, it gets a bit airy-fairy up through there, but the mines still sit, well, apart from Wiluna, which sits on a black one, haven't figured that out yet. So those white patches down there absolutely, definitely have got something to do with mineralisation. Well, they are the source of the mineralisation on the surface if you believe in the power of coincidence. They're no coincidence. The other thing is that as we could see on the other one, the change between the brown upwelling mantle and the remaining giant ring structures actually where other, I'm talking about major mines, sit on. Tropicana, Gruyere, all around that area, particularly where you've got white blobs, they should be very prospective, like Gruyere is and Tropicana is. So carrying that forward in terms of exploration targeting, the rings, the brown areas and the white areas under the mines, they make, they're the target areas. So if you carry that through to the surface, that is actually the an enhanced Landsat showing large ring structure. And these are the areas that I would be out there targeting right now if I had the money. So up to the Pilbara, I'll go very quickly through these. I think I might be running out of time. So hopefully there's none of you out there that can't see this ring structure here, which I often find that the smaller you make these things, the clearer they are to see. And so that's that one made small Coondawana ring structure. That's an Aboriginal community that sits right in the middle of it. The same thing applies if you look on the seismic section, 20 degrees south seismic section, you can see the dark vertical fluid pathways, not quite so good out on the edge, but ones sitting out near Telfer aren't too bad. And the ones up through the centre here are actually pretty strong. But this is a long way off the centre of this ring structure. all of the banded iron formation mines, irrespective of how they got there, they all sit within that ring structure. Like I'm talking about, all of those banded iron formations sit right within that ring structure. A lot of discussion on how did banded irons form. Well, I'm taking a fair guess that very strong iron-rich solutions have come up from this big ring structure, which actually goes right down to 300 kilometres. And that's the iron source for the banded iron formation on top. Go down to 300k depth, the Coonawanna impact has totally disappeared, but you've got this almighty great big one that sits down there, around there, and probably easier to see on the smaller. So that's an example of probably the original craton forming later heavier bombardment impact. You also can see this north-south zone. That's a continuation of the Norseman-Wiluna belt, and it's also the one that we could see on the 75. That's the mines. Other thing of interest was in America, in the Carlin Trend, you've got the mines are on a dome and basin. They form on the domes, and this area under the iron ore mines looks for all the world like what I've been able to pull up of the Carlin Trend dome and basin structure, as does Telfer. Telfer looks like a dome and basin structure as well. Well, we know Telfer's on a dome. So those domes probably originated long, long way down. Same thing, that's your target areas. And that's the target areas on the surface. That particular ring that you can see in the Landsat, that inner one correlates exactly pretty much with the Coonawanna impact down at 75k. Mount Isa, this is enhanced Landsat. So there's a ring structure there, relatively well defined over about half of it. They're the mines. So the mines all around Mount Isa, that's Mary Kathleen, that's Mount Isa, and then there's a ring. These are the only the ones that are getting mined at the moment, and they're the biggest ones that are in that area. And they basically form a ring inside that ring. Copper, uranium, silver, lead, zinc. And that's the same thing. Surface Landsat's the white one, the yellow ring is the, well, I didn't put a blank one up because I'm out of time, but effectively that's a ring, and then the inner ring actually looks like a thumbprint that sits in there, and these mines sit right around the edge of it. MacArthur River, Century, they sit on this big ring that runs there. As you go down to 150k, the ring now has disappeared, it's bottomed out, and you've got a ring off to the east, and the big rings that we saw on the Australia-wide one sitting out to the west, and then two rings. But everywhere where you've got the rings and the linear structures, where they all meet and they're the most complicated, that's where you've actually got the mines, simply because there's a fluid pathway that runs straight through. That's down 300k again, so it's actually the same thing. You've got white blobs, mines, even the outliers seem to sit on them. Mount Isa on that one, and these mines on others. And once again, that's the targeting that I would use in the Mount Isa belt. Like, they took me a quarter of an hour to do. Not rocket science really, but could be billions and billions of dollars worth of material in there. And the Gawler Craton, the Proterozoic just doesn't come out as well on tomography, but still Olympic Dam definitely sits on a ring. Broken Hill on a half-baked ring, but definitely on a lot of linear structures. Mantle, intrusion coming up, 3 of them there. Once again, the mines sit around the outside edge of them. Broken Hill sits on a very strong north-south lineament and right between 2. These mines out here, there's a prominent hill, that one I think, and the other one of Resolute out further. They sit on the boundary, on the white structures, and also on the boundary of the brown and the grey. Like, it's just so consistent it can't be a fluke. So that's the targeting that I would use there. Also, maybe a half-baked Diamond Basin sequence there, right north of Broken Hill. Should be up Tibooburra way somewhere. Got a mate who's got a show up at Tibooburra, he might be interested in that. North American Craton, so we'll go up there now. This one here. This is a sort of a half-baked, I really didn't take much time over it. I should have taken more time over it, but there are a lot of ring structures showing in the tomography on North America. And I've given them all names, which is mainly the state that they occurred in. And I've also had a closer look at the Abitibi belt, mainly because I've been very interested in the Abitibi belt because it's just such a rich, small belt. Why does it occur, and why does it occur east-west? Well, we know that it occurs east-west because running along the Cadillac-Dexter break. I got interested in it. Oh, the other thing is that once again, North American surface geology is all accreted geology, north-south. Nothing like what you see down in the lithosphere. So this is the Abitibi belt. Yeah, the first lot of people that have seen this representation of the Abitibi belt. Absolutely, definitely big ring structures there. I got interested in it because I saw ring structures in gravity back 10 years or more ago. Thought, oh, I'll put that off to one side, and when I get round to it, I'll have a look at the Abitibi belt. So in terms of ring structures, there's a little ring structure in there, a bigger one there, bigger ring of it around there, another ring structure there. They get a bit fuzzy and your eyes go a bit weird, and another one there. The trouble is you can't get all the information to show up on one slide, so I've actually picked an intermediate slide here which shows this particular ring structure in a bit more, well, perhaps a little bit more believably. The other thing I do to convince myself perhaps that they're not just artefacts of my imagination or my mother's faces, the skeptics would tell you you're looking at, is I'll do a mirror image of it. And if something like an owl's face pops out at me, I know that it's a ring. If something like a chevron or whatever pops out at me, I know that it's just linear structures. And I think very definitely an owl's face popped out at me there, apart from the fact that it shows up in the gravity near the surface. The interesting thing about the Sudbury mine too, which is supposed to be a late 2000-ish million years ago thing, actually lies on this almighty great ring that sits around there. The Sudbury sits like Mount Isa in particular and like Kalgoorlie, and that sits right in between a whole series of rings. and it's sitting on a nor-nor-west structure and an east-west structure and a lot of rings, and that's absolutely the structural geology of Kalgoorlie. And so thought, oh, well, I'll enhance the actual ring structures that are under Abitibi, so I've enhanced them. And yeah, at what's 100k down, like Kalgoorlie, like the Yilgarn, like all of the other fields that I've looked at, the plumbing system's obviously absolutely dead vertical because the mines are sitting right on the big structures. Like I'd be very surprised if they sat off over here, because they haven't so far. Like totally consistent information. It's not a small field, the Abitibi, 170 million ounces and counting. And lots of copper, silver, lead, zinc. Hemlo's another big mine that was found later. It sits on structures. I mean, you can do the same exercise with, and I haven't yet, but I will, with the Abitibi belt from 300k up to the surface. I'll bet you that it's the same system, because the whole lithosphere formed at the same time, and it's going to have the same mineralising systems over all of Earth. There's no reason why one area should be different from the other. We'll go across to China. Once again, the surface geology's got nothing to do with the big ring structures that sit underneath. It's the Chinese, the North China craton, looks like the bottom of it's actually been, well, I've seen written that the bottom of it's actually been wiped off, but the bottom of it hasn't been wiped off, it's just been in situ replaced by the mantle, because this big ring structure goes right down to 300k, exactly looking the same as that, but at that point it's supposedly in the mantle. So that's the ring structure, which looks for all the world like that moon one that I showed way back with the blue and the different colour, different ages. So that's the original ring, and the later lavas, which is this browner colour, actually fill the annulus of the ring. And that's the mines around that particular ring. And I haven't included it here, but these concentrations of mines here and here and here are where there's brown coming up from underneath at 300 kilometres depth. And where the brown doesn't come up from underneath at 300 kilometres depth, you don't get any of the gold mines. So summary of the genesis of the lithosphere in all of the places I've seen is that it's formed between 4.2 and 3.8 billion years ago during the late heavy bombardment. A bit of a sketch of how it formed, as I showed on the more detailed one. Impact, lots and lots of lava coming out and making mares in the craters. So these would have all been mares at some point, hence the very strong brittle structures in them. And then after that, from 3.8, which is roughly the oldest crust, there's older little bits, but there's a lot of 3.8, right through to the present day. It's basically the little thin crust is formed on top. And it is little and thin. And the only thing I'll focus on here is the way that these cratons have actually been preserved, is that the continuous strong isostatic pressures pushes they actually end up a lot lighter, because all the heavy rocks been extruded as lava and then been eroded off. And so that's all gone off to the side, and the isostatic pressures pushing the cratons up. Takeaways of the talk: giant ring structures exist from the surface to at least 300k. All the lithospheres I've seen so far have been absolutely continuous. And they form between in the late heavy bombardment, being absolutely the only thing that could have created those huge big structures. And the most important thing is the mineralising systems. So superheated fluids, which are probably closer to 3,000 degrees centigrade at 300 kilometres depth, they come down and they're only 20 degrees at the top. So you're going to scavenge minerals on the way up, and they'll deposit them on wherever they find a likely rock or structure. So I would guess that if we could just work our way down all these structures, we'd just find deposits the whole way, which is why you get deposits in all ages on Earth. And the other thing is that specific metals are related to, very definitely related to specific impacts or giant ring structures. Thank you for your attention.